Okay, this problem says, suppose that you have a coffee mug with the circular cross-section and vertical sides. What is its inside radius if it holds 375 grams of coffee when filled to a depth of 7.5 centimeters? Assume coffee has the same density as water. Okay, so the density is 10 to the power 3 kgs per meter cube. Or actually, we'll write it as 1 gram per centimeter cube. Okay, so that's the density of water. This is in SI units. This is in CGS units. Okay. So there's the coffee mug, and 7.5 centimeters is 3 inches. Yeah. What is the radius is what we want to find. Yeah. So the volume is area of cross-section times the height. Area of cross-section is pi r square times the height. And density is mass divided by volume. So r square is mass pi rho h. Mass is 375 grams, pi 1 grams per centimeter cube. H is 7.5 centimeters. So you see the grams will cancel. This centimeter you'll get centimeter square, which will come up, and then out the square root you get the answer in centimeters. So this will equal okay, so the radius of the cup is 4 centimeters. So this problem says a trash compactor can compress its contents to 0.35 times its original volume. Neglecting the mass of air expelled, by what factor is the density of rubbish increased? So this is mass divided by original volume, and the new density will be new volume, which is mass divided by 0.35 times V naught. So the new density is 1 over 0.35 times the old density. So 2.86 times. And you guys have seen this on highways where they crush cars and then they're transporting them. And the reason for doing that is you can transport more cars that way. Okay, a dam is used to hold back a river. The dam has a height of 12 meters. 12 meters is roughly 3 times this height. Okay. Roughly the height of this building. well, yeah, and a width of 10 meters. 10 meters is from here to the wall. Assuming the density of water is 1,000 kg per meter cube, determine the net force on the dam. Why does the thickness of the dam increases with depth? Because the force on this strip is greater than the force on this strip, and so you have to have a greater wall thickness. Okay. So we'll find the net force on the dam. So we'll call this force dF. Okay. And then the net force will be the sum of all those little forces. What is that little force? That little force is the pressure depth at that depth times the area of this strip. Okay. That's the area of that strip. What is the pressure? Okay, now see the pressure at this depth. The pressure at this depth is P naught plus rho GH. Okay, but there's atmospheric pressure here as well. So really the force you have to apply is just gauge pressure. This pressure minus that pressure. Okay, so pressure is, okay, so you have to apply gauge pressure, rho GH times, okay. Okay, so the net force is rho GH. Area is dy times width. Okay. What is h? So we are measuring y from here like that. So h is actually, let me use this notation. Oh, capital H was the total height. Okay, sorry. Capital H was this height, so this is rho g little h, okay, and rho g little h is h minus y. We are setting it up as an integral. Okay. And what does y go from? 0 to h. Okay. All right, so rho GW so the net force is rho GW H minus H by 2. Rho G. W times H is the area, total area of the, and this is H by 2. Okay, what this is, see, this is the average pressure. This is the average pressure on the wall. Okay, the average gauge pressure. Average pressure times the area of the wall is the force on the wall. Okay. So, assuming bicycle tires are perfectly flexible and support the weight of a bicycle and rider by pressure alone, calculate the total area of the tires in contact with the ground. If a bicycle and rider have a total mass of 80 kg and the gauge pressure in the tires is 3 times 10 to the 5 pascals. All right, so I'll just draw one wheel. And let's say this much of the wheel is in contact with the ground. Okay, now, so there is always air underneath there. So there's atmospheric pressure outside. And this is absolute pressure, which is so this is absolute pressure, which is P naught plus gauge pressure. This is the pressure outside. Okay. All right. So we're looking at this portion of the wheel. That portion of the wheel is at rest. Well, there's the weight of this guy, and the ground pushes this piece of rubber up with the force equal to the weight. Okay, so the ground is pushing, the normal force is equal to the weight being supported. Okay, this piece of rubber is not going anywhere. The net force on it is 0. So the gauge pressure on this thing, the force due to the air, which is the gauge pressure times the area, should match that. Okay. All right, so the gauge pressure times the area of the wheel in contact should equal the weight being supported. And of course, if you have 2 wheels, then that's the total area from the 2 wheels. Okay, even though we've drawn just 1 wheel. Okay. So you can see that the smaller the area of contact, the higher the gauge pressure you need. Okay, so that's why if you have seen road bikes are very thin tires. Okay, the area of contact is smaller, they have to be pumped to a higher pressure than mountain bikes. Okay? And those fat tire bikes, even less pressure. Okay? All right, so the gauge pressure, and so if you're lifting a heavy load, if your vehicle is a heavy load, what do? I mean, you can't have an arbitrarily high gauge pressure, so how do you fix that? You increase the number of tires. So that's why semis have more axles. Okay? So the more weight you have to support, the more tires you will have. So the gauge pressure is mg. Oh no, we're trying to find the area. Okay. So the area is mg divided by the gauge pressure. So this is 80 kgs times 9.8 meters per second square divided by 3.5 into 10 to the power 5 pascals Newton meter square. Yeah. And what we'll do is we'll borrow 1, so we'll make this 35, 10 to the power 4. That'll come to the top. So 80 into 9.8. 22.4 into 10 to the power minus 4 meters square. And this is a centimeter square. So this is 22.4 centimeters square. So roughly 5 centimeter. Okay. So that's the area. So, okay, so 4.73 centimeters square. So that's roughly a square of 2 inches. So that's how much tire is in contact. Okay, this problem says, what force must be exerted on the master cylinder of a hydraulic lift to support the weight of a 2,000 kg car? So 1 kg is 2.2 pounds. So this is a 4,400 pound vehicle. So it's an SUV resting on a second cylinder. The master cylinder has a 2 centimeter radius, and the second cylinder has a 2 centimeter diameter and 24 centimeters. So this is a factor of 12, and so the area is 12 square larger, 144 larger. So this is a force multiplication of 144. So every pound of input force, you're getting 144 pounds of output force. Okay, so this is called the mechanical advantage of the machine. Okay. Okay, so this is A2, F2. So F2 equal to A2 over A1. And in terms of diameters, D2 square over 4 pi D1 square over 4. Okay. And this is 24 by 2 square over. Okay, so you see the output force is 144 times the input force. Okay. So we'll calculate that again. So mg is the output force, is equal to 1/44 the mg. I mean, I can calculate the numbers, but the numbers won't mean anything, you know. Okay, 136 newtons That is 13 kg, 25-pound force. So you're applying a 25-pound force and lifting up a 4,500-pound vehicle. Okay? So you can do that with a foot pump. Okay, we'll do 2 more problems. So let's calculate this. So you guys have bought helium balloons, and when you let go, the helium balloon accelerates upwards. Why is that? I'm sorry? Yeah, and so the buoyant force is greater than the weight of the balloon and the helium, and so it keeps accelerating. And it'll keep accelerating. Till what point will it keep going up? Will it accelerate?
Space.
Till the density of the surrounding air equals the density of the balloon and the helium. And then the velocity will become constant, and then it'll eventually stop, okay, because of friction. So the steady state is where it'll go and stop where the surrounding air density is equal to the density of the balloon. Okay? All right, so calculate the buoyant force on a 2-liter helium balloon. So here's the balloon. So there's the buoyant force, and there's the weight. Yeah. What is M? M is given the mass of the rubber balloon, mass of the balloon plus mass of the helium. Okay. And the mass of the balloon is 1.5 grams. And what is the mass of helium? How do we find the mass of helium? Okay, 1 mole of helium weighs 4 grams. Okay, and how much does 1 mole of helium occupy, volume-wise?
1 cubic meter.
No. There you go. Thank you, my friend. 22.4 liters. A mole of a gas, it's STP, occupies 22.4 liters. Okay. And we are assuming this, so even though the problem doesn't give STP, standard temperature and pressure, yes, so the mass of helium is 2 liters divided by 22.4 liters times 4 grams. Okay. So 1.86 grams is the mass total being supported. What is the buoyant force? What is the buoyant force? It's the weight of the displaced fluid. What is the displaced fluid?
Air.
Air. Very good. Okay. So density of air times the volume displaced times gravity. And the density of air is 1.3 kg per meter cube. Volume is 2 liters, and a liter is 1,000th of a meter cube times G. Again, G is 9 point. There's the buoyant force. So, and now we'll calculate the weight in newtons. So M it was 1.86 grams, 1.86 into 10 minus 3 kgs times 9.8 meters per second squared. So the net force is, yeah, so there was the balloon, there's the buoyant force, and there's the weight. As promised, the buoyant force is greater than the weight, okay? And so the helium balloon rises up. Yeah. So also for a hot air balloon, the buoyant force is greater than the weight of the hot air balloon. Okay. All right, so here's an interesting problem. Every few years, winds in Boulder, Colorado attain sustained speeds of 45 meters per second, about 100 miles per hour. Okay? When the jet stream descends during early springs. Okay? So jet streams are rivers of air flowing in the upper atmosphere at a height of maybe 11, 12 kilometers. And these rivers are about I don't know, maybe 3 kilometers across. So from here to the speedway, so think of a river that wide, and this air is flowing anywhere from 100 to 200 miles an hour. Why do we care about this? Do you guys know what is the speed of a plane, of a commercial plane?
500 miles an hour?
Yeah, so it's about 600 kilometers per hour. So here's a jet stream. So if you want to go from here to there, just fly in along with the jet stream. And now, you're getting a push, a 30% push. Okay. So you save on fuel. Okay. All right, so there are the jet streams. Okay. So approximately, what is the force due to the Bernoulli equation on the roof having an area of 220 meters square. 220 meters square is roughly the size of this roof. Okay. Okay, so the deal is the following. The problem is essentially the following. Okay, so you saw that if air blows faster here, the pressure is lower here. The air inside the house is, of course, is still, and the pressure is higher here. It's atmospheric pressure. Okay, and so there's a net upward force on the roof. Okay, and this force could be large enough to take your roof off. Okay, this is how a plane gets a lift too. I mean, okay, so the air above is flowing faster than the air below. Okay, so Mr. Bernoulli says, okay, so we'll say this is 0.1, 0.2. Mr. Bernoulli says P1 plus 1/2 rho V1 square plus rho GY1 is equal to P2, the pressure, plus 1/2 rho V2 square plus rho GY2. Okay, we'll say Y2 is equal to Y1. Okay, so these guys cancel, and what is V2? V2 is the velocity of air in here. What is that?
0.
0. Okay. So what is the upward force? The force is P2 minus P1 times the area of the roof. P2 minus P1 is 1/2 rho, and that's equal to 1/2 rho V1 squared times the area of the roof. Yeah. All right, so 1/2 rho, the density of air is 1.3 kgs. All right, they give you a 1.14 kgs. Okay, so we'll use that value. Did you have a question? Okay. All right, so this works out too. Newtons. So if you divide that by 10, that's 2.5 times 10 to the 4 kgs. That's roughly about the weight of 3 school buses. Okay. So you're pushing upward on the ceiling with a force of 3 school buses. All those hinges better hold on to it real hard.